Good afternoon, everyone. My name is Hui Tan. Today I will introduce a new inversion method to calculate tsunami flow condition based on tsunami deposit. For this talk, we include 5 different parts. First, I will briefly introduce TsuSpeedv1 model and EnkF method. And then I will talk about the test case about the Sous velocity, and then talk about the inversion result for this test case. And then I will talk about the error analysis about this test case and give a summary about this talk. First, let's talk about the TsuSpeedv1 model. Original TsuSpeedv1 model is an inversion model to calculate flow speed. But for here, we only use the sediment formation part as a forward model to calculate sediment flux. There are a lot of different assumptions in TsuSpeedv1 model. For the sediment formation part, we have 3 major assumptions here. First of all, we assume there is a simple topography with gentle slope. Secondly, all sediments in TsuSpeedv1 model will be transported as suspended load. Finally, sediment flux will calculate in a controlled water volume. So for EnkF method, the full name of EnkF method is the Ensemble Kalman Filter method, which is widely used in weather forecasting. This is a data assimilation method. We will present unknown parameter we want to invert as a possibility density functions. For each ensemble point is a point in the state space. I will talk about what's the state space later. The right flow chart here shows how EnkF method and TsuSpeedv1 model works. First, we will have an initial gas. The initial gas includes the mean of initial gas, the range of initial gas, and the distribution type of initial gas. We use different sample methods to sample the initial gas to get initial shear velocity. When we get the initial shear velocity, we will use TsuSpeedv1 model to calculate the sediment flux. We compare this sediment flux with the observations. The observations can come from field observation or other models. For this test case, we will use the sediment flux from the TsuSpeedv1 itself. When we get these 2 types of data, we will use EnkF method to calculate the covariance and the Kalman matrix to correct the shear velocity. When we get the corrected shear velocity, we will go back to the second step to continue this loop. The number of steps of this loop is based on how many field observations we can get. This is a figure showed ideal test case, show how EnkF method works. First, we will have an initial ensemble present a preview PDF, and also we have the field data. We will use EnkF method to calculate the covariance and the Kalman matrix between the preview PDF and the field observation data to modify the initial ensemble to get the modified ensemble. So for each PDF, for each time step, here is a state space. The state space can be the unknown parameter itself, and also can be some other variables related to this unknown parameter. So now let's talk about idealized test case about shear velocity. This figure here shows how TsuSpeedv1 model to reconstruct the sediment grain size distribution for an entire tsunami deposit. The green line here is the model result. The red point here is a field data. Generally speaking, the model result fits well with field data. This figure here shows more details in tsunami deposit reconstructed by TsuSpeedv1 model. We also use this figure. This figure also can show how we compare and compute sediment flux from TsuSpeedv1 model and field observation. We separate this entire tsunami deposit into 4 different layers. For each layer, we consider as a time step. The sediment flux for a given grain size classes here will be based on the percentage of these grain size classes and the thickness of this layer. This is an inversion result for this idealized test case. Because this is idealized test case, we already know the real shear velocity for this test case is 0.5 here. Ideally, the final inversion result should be only one given value equal to 0.5. But however, because of the influence of the model error and the uncertainty in the field data, the final inversion result will become a possibility distribution here. For this test case, we can say we have 19% guarantee the shear velocity should be between 0.48 to 0.52. So based on this test case, we do some error analysis here. Before we talk about the error analysis, I will talk about some general information about error. There are a lot of different type of error in the inversion model result. We have two major types here. Observed error, which comes from the field data or input data. The model error from the inversion model itself. For the observed error, we also have two different type error. Systematic error, which comes from the data you want to measure, and the type of data you want to measure, and the method you use to measure your data. And another measurement error, which comes from the tool or machine you use to measure your field data. We also propose a simple way to quantify the uncertainty between the calculation results and the true value here. We also propose an error model for the observed error. For the model error, in the future work, we will quantify the model error, which is much more difficult than the observed error. For this observed error is a related error. It is based on the systematic error and the measurement error present as greatest possible error, which is equal to the half smallest interval of your machine. And for this test case, we measure the weight grain size distribution. The weight grain size distribution is based on the total weight of your sample, the number of grain size classes you divide, and the number of sediment layers you separate in your sample. So this flow chart shows how we do the error analysis. First, we input the number of grain size classes and the number of sediment layers into the error model to calculate the observed error. And also we input, when we get this observed error, and we input other information for the model setting to run the TsuSpeedv1 model and the EnkF method to get the inversion results with uncertainty. We quantify the uncertainty. This figure here shows how the observed error will influence the conversion and the inversion process. Again, this one for this ideal test case, the real shear velocity for this test case is 0.5. So each grain line here presents a shear velocity example. The red point here is the mean of the shear velocity. We will look the detail in the fifth step and the final step. The left figure here shows the inversion result of the fifth conversion step, and the right figure shows the the inversion result for the fifth step, and the left figure here shows the final inversion result. Compare these two figures, we can find with increasing the conversion steps, the range of the inversion, the range of the shear velocity will decrease. Again, the real shear velocity here is equal to 0.5, shown as the red line. We also found some interesting things during we do the error analysis. This figure here shows the relationship between the number of samples we used, or input to the inversion model and the uncertainty of this model result. With increasing the number of the samples we use in the inversion model or TsuSpeed model, at first the uncertainty will decrease because we input more information to the inversion model to hope to get the right answer. At some point, the uncertainty will increase again because when we input more samples into the inversion model, it means we input more errors into the inversion model. So this relationship suggests us when we want to use the field data to get the inversion result by the inversion model, first we should consider the burst number of samples we should use for this inversion model. We do the same thing for the water depths. We find the burst number of samples is a little bit different from previous one, which indicates the burst number of samples we used in the inversion model is based on the type of unknown parameter you want to invert, and it's also the forward model you employ in EnkF method. So finally, I will make a summary about this talk. First, TsuSpeed and EnkF method can quickly invert the tsunami flow depth and the flow speed. Secondly, the uncertainty in the final result will follow a possibility distribution. In order to reduce the uncertainty for the final inversion model result, we should figure out the burst total number of samples we used. The burst number of samples we used is based on the type of unknown parameter you used and the forward model you employed in EnkF method. Thank you very much.
Any questions? It's time for one question. Oh. Well, thank you very much.